Imagine standing at a bus stop on a, really busy city street, just waiting for your morning ride,
Oh, yeah, we've all been there.
right? And the bus pulls up, the doors open, and as it lurches away from the curb to merge back into traffic, you're just hit with that familiar, uh, choking cloud of thick diesel exhaust.
Ugh, the absolute worst way to start a morning.
It really is.
Huh.
But, well, what if I told you that simply moving that painted signpost, like 20 meters down the street, could practically cut that cloud of pollution in half?
Wait, really? Just 20 meters?
Just 20 meters. Welcome to another episode discussing the research projects developed by the Applied Computing Research Group, GCA. Today, we are heading to Brazil to unpack a study that, honestly, completely reframes how we look at urban transit, smart cities, and the air we breathe on our daily commutes.
It's just a remarkable piece of engineering and data science. I mean, we spend so much time talking about futuristic, utopian city planning,
Yeah,
right?
constantly. Flying cars and hyperloops.
Exactly. But the team behind this research, they chose to look directly at the messy, imperfect reality of how our cities operate right now.
Which is so refreshing.
Yeah.
And we need to highlight the minds behind this work right out of the gate. So this study comes from Luciana M. Cardoso,
Yeah.
Rafael Z. France, Luis Antonio Rocia, Sandro Sawicki, and Fabricio Rus France.
And they are all researchers at Unijuí University down in Brazil.
Yes, Uniju University. And the mission they laid out here is something, honestly, every transit authority everywhere should be dissecting. They are tackling this massive question: how do we dramatically reduce pollution from public transit without needing to buy, entirely new fleets of expensive futuristic vehicles?
Because that reality check is vital. The ultimate goal here isn't just to write some theoretical academic paper that sits on a shelf.
Right, it's about real-world application.
Exactly. It's about using raw, hyperlocal data to change the physical behavior and the routing of the buses we already have on the road today.
Because when you hear a term like smart mobility, it is so easy to picture, like silent, ultra-sleek electric buses gliding down these beautiful neon-lit streets.
Yeah, the brochure version of the future.
Exactly. But the researchers ground this study in the actual current economic and physical landscape. They provide some context on the public transit situation in Brazil, and it paints a very stark picture of why this research is so urgent.
Yeah, let's look at the baseline numbers they analyzed. In Brazilian cities with populations over 60,000, public buses account for a staggering 85.7% of all public transport journeys.
Wow, 85.7%, that's huge.
It is. I mean, it means the vast majority of the urban population relies on this single mode of transport just to get to work, to school, to hospitals. And consider the national fleet. There are roughly 107,000 public buses operating in Brazil.
That is just a massive amount of heavy machinery. So I have to ask, out of those 107,000, what percentage are fully electric, zero-emission buses? I imagine it's pretty small.
Well, small is kind of an understatement here. Out of that entire national fleet, only 427 are electric.
You're kidding. 400 out of 100,000.
Yeah. And to concentrate the issue even further, 269 of those are operating in literally just one city, São Paulo.
So that leaves, over 100,000 buses relying on traditional internal combustion engines.
Correct. The overwhelming majority are heavy diesel engines. And when a heavy diesel engine is, hauling dozens of passengers around a dense city grid, it's just constantly emitting carbon dioxide, carbon monoxide, and nitrogen oxides into the immediate environment.
And those are gases that have direct, measurable impacts on public health.
Oh, absolutely. They wreck urban air quality.
It's like waiting for a fully electric bus fleet to save the environment is like waiting to win the lottery to pay your rent.
That is a perfect way to put it.
Right. Yes, electric vehicles are the long-term goal. But cities do not have the budgets to just scrap 100,000 functioning buses overnight and rebuild their entire electrical grids to charge them. We need a solution for the hardware we're stuck with for the next 10 to 20 years.
Which forces transit planners to ask a totally different set of questions. If we cannot change the engine itself, how do we optimize the operation of that engine? And this is what leads the researchers into the science of eco-driving.
Okay, so eco-driving. When I first encountered that term in the study, my mind went straight to, Vehicle maintenance.
Sure, like oil changes and tire pressure.
Exactly. Making sure the diesel injectors are clean, keeping the tires inflated to the right pressure, maybe using a fancy synthetic oil. But the study pushes past the mechanical side and points straight at the human element.
Well, vehicle maintenance certainly matters, obviously, but the researchers highlight that the driver's real-time behavior is, it's the ultimate variable here.
The person actually behind the wheel.
Exactly. Despite decades of advancements in internal combustion efficiency, the person pressing the pedals dictates the fuel economy. Behaviors like pushing the speed limit, rapid acceleration, harsh braking, all of that causes fuel consumption and those toxic emissions to spike dramatically.
Okay, I actually want to push back on that a little bit.
Go for it.
If you're driving a 30,000-pound bus in stop-and-go traffic, and your route forces you to stop on a steep incline, you don't really have a choice, do you? You have to floor the accelerator just to overcome gravity.
Yeah, just to get the thing moving.
Right. So is it really fair to blame the driver's habits when the physical route might just be setting them up to fail from the start?
You've hit on the exact friction point this study investigates, and honestly, the data entirely supports your skepticism.
Oh, it does.
Yeah. The researchers cite previous work in their source material, specifically studies by Karice and colleagues, and also Oziner and Eskin, which measured the physical impact of topography. They found that road gradients like steep hills can actually double a bus's emissions.
Wait, double the output just from driving up a hill?
Yes. And the physics behind it are straightforward, but they're punishing. An object at rest requires a massive amount of energy to get moving. So when you add a steep incline, the engine has to fight both inertia and gravity at the same time.
Which means the driver has to really step on it.
Right. They have to dump a massive amount of diesel fuel into the combustion chamber to generate enough torque. And because the fuel is being dumped in so quickly, it doesn't burn cleanly or completely.
Ah, which causes that thick black smoke you sometimes see.
Exactly. That's a massive surge of nitrogen oxides and particulate matter.
So the geography essentially dictates the mechanical strain.
It does. And the researchers identified what they call critical driving zones. These are the physical areas roughly 200 meters around every bus stop.
Oh, I see. Because that's where the bus is constantly decelerating, idling, and then accelerating hard to get back into traffic.
Precisely.
Which means the absolute highest concentration of toxic exhaust is being pumped out exactly where people are standing on the sidewalk waiting. That is so wild. But if the route's physical layout and the stops are forcing this, how does a city planner fix it? Like, they can't just flatten a hill.
No, they can't flatten the hills, but they can adapt to them. To do that, however, they need hyperlocal, second-by-second data. A planner can't just guess where the bus is struggling.
Right, you need hard numbers.
Exactly. They need to measure the exact correlation between the road gradient, the driver's behavior, and the exhaust pipe.
And I know the researchers realized standard data wasn't going to cut it here. So what exactly did they build to measure all this?
They engineered a custom, low-cost Internet of Things, or IoT sensor device, specifically designed to be mounted on these public transit buses.
And it's basically a custom-built tracker.
Pretty much. It's a highly practical piece of hardware made up of 6 distinct modules. There's a power module and a microcontroller acting as the brain, of course. But the core data collection happens through 3 specific sensors. First, a GPS module that tracks latitude, longitude, speed, and most importantly, altitude.
Oh, because they need the altitude data to map out those steep hills and road gradients you mentioned.
Exactly. The second is a gas module, which physically measures the ambient carbon dioxide, carbon monoxide, and nitrogen oxides in real time. And the third is a climate module tracking temperature and humidity.
Wait, why do they need to know the humidity and temperature? Doesn't the engine run the same no matter the weather?
Actually, no. Weather significantly impacts engine combustion efficiency. Cold, dense air mixes with fuel differently than hot, humid air.
I had no idea.
Yeah, and that alters the baseline emission levels. So the researchers needed to account for every single variable. Now, all this data is gathered by the microcontroller and passed to the final piece, the communication module. And this is where the engineering gets really clever.
Oh.
Well, they don't use standard cellular networks or Wi-Fi to transmit this data back to the central server. They use a LoRaWAN network.
Okay, LoRaWAN. Long-range wide area network. I know the study mentions this operates at a 915 megahertz frequency in Brazil, but why use this specific technology? Like, why not just pop a 4G SIM card in the device and stream it like a smartphone does?
It really comes down to the physics of radio frequencies and the messy reality of a city landscape. Standard 4G or 5G cell networks operate at very high frequencies, and high-frequency waves are tight and fast, which is great for streaming YouTube, but they get easily blocked or scattered by solid concrete buildings.
Oh, right. Or tunnels, or just electrical interference.
Exactly. But a 915 megahertz frequency has a much longer, wider wavelength.
So those longer waves can basically bend around concrete corners and push through urban obstacles way better.
That's it. Plus, cellular networks require devices to constantly handshake with cell towers, which drains battery power rapidly. LoRaWAN is specifically designed for long-range, low-power data collection.
Those more efficient.
Way more. It allows the sensor on the bus to continuously ping the server with tiny, simple packets of data, just raw numbers for speed, gas levels, altitude, without needing an expensive monthly data plan or some massive power supply.
It really is an incredibly efficient system. But, reading through the study, the detail that stood out to me as just the most clever piece of practical engineering wasn't even the network. It was where they decided to physically attach this device to the bus.
Ah, yes. The placement.
Right. They didn't put it near the driver's dashboard or down low near the exhaust pipe. They insisted it must be installed on the top rear of the bus. Why the roof?
It is all about the aerodynamics of a moving box. As a massive rectangular vehicle like a public bus pushes forward, it displaces the air in front of it, right?
Right. It pushes the air out of the way.
And this creates a specific pattern. The air flows over the flat roof and around the flat sides, and as it reaches the back of the bus, those airflow lines curve parabolically inward.
Parabolic airflow. Okay, so the air kind of swirls together in a wake right behind the vehicle.
Yes, exactly. It creates a low-pressure zone at the very rear of the bus. And that low-pressure zone actively pulls the hot exhaust gases coming out of the tailpipe upward, while simultaneously pulling the ambient city air inward.
Oh, wow.
So by placing the sensor at the top rear corner, the researchers are positioning it right inside this perfect natural mixing bowl. It provides the most mathematically accurate average sample of the exhaust the bus is creating, combined with the air the environment is actually absorbing.
That is so smart. It's kind of like putting a fitness tracker on the bus, but making sure you strap it exactly to the wrist where the pulse is the strongest. Like, you wouldn't wear a heart monitor on your shoe and expect accurate cardiovascular data.
That is a brilliant analogy. You have to place the sensor where all the physical signals converge.
Right.
So picture the setup. You have this bus driving its regular daily route, dealing with passengers and traffic. Meanwhile, that sensor is riding up in the parabolic airflow, continuously beaming perfectly synchronized data about speed, altitude, weather, and toxic gas levels right through concrete buildings via that 915 megahertz frequency.
Which creates a massive new problem for the transit authority, doesn't it? Because now they have a server filling up with mountains of raw second-by-second data. How does a city planner actually make sense of that without getting completely overwhelmed?
Well, that is where the computational model comes in. But the first step isn't optimization, it's ruthless data cleaning. The researchers stress that to find a baseline of quote-unquote normal behavior, they have to filter out the anomalies.
What kind of anomalies are they tossing out?
Days with heavy rain, for example. Rain forces drivers to slow down abnormally and changes visibility, which entirely alters their driving habits.
Makes sense.
They also strip out data from days with major traffic accidents, political demonstrations, or public festivals. Basically, they remove any data corrupted by unusual, severe congestion.
Okay, I have to jump in here.
Yeah.
Because cities are messy by definition. You can't just delete traffic from your transit data. I mean, if we filter out rainy days, traffic jams, and parades, aren't we just building a mathematical model for a perfect utopian city that doesn't actually exist?
It sounds like cheating the data. I know.
Yeah.
You'd think ignoring the rainy days makes the whole model useless, but think about what a transit planner can actually control.
Okay.
They are trying to identify the impact of the route's permanent physical geography, the hills, the curves, the distance between stops, and the baseline eco-driving habits of the driver.
Right.
So if you include a day where a parade blocked the main street for 3 hours, the algorithm might look at the data and mistakenly conclude that a perfectly flat, straight road is actually a high-emission critical zone simply because the bus sat there idling in uncharacteristic traffic all afternoon.
Ah, I see. Okay, so you have to remove the uncontrollable chaos of daily city life so you can clearly see the underlying structure of the route. You're trying to fix the permanent bones of the system, not the weather.
Exactly. You fix the bones. Once the baseline data is cleaned and isolated, the researchers apply something called multi-objective combinatorial optimization.
which sounds incredibly intimidating. How does that math actually work in this context?
It sounds complex, but in any optimization problem, you're just trying to find the best possible solution given a set of constraints. The challenge here is that the transit authority has multiple conflicting objectives.
What are they?
Well, objective 1 is to get the passengers to their destinations on time. Objective 2 is to minimize fuel consumption and toxic emissions.
And those are fundamentally at odds. Like, if you only cared about air quality, you'd make the bus drive at 5 miles an hour everywhere. But if you only cared about the timetable, the driver would just floor the accelerator every single green light.
Precisely. And this is where the model seeks out what is called the Pareto optimal frontier.
I love the concept of the Pareto frontier. It's kind of like mixing hot and cold water in a shower.
How so?
Well, you have two competing goals, right? You don't want to freeze and you don't want to get scalded. The Pareto frontier is that tiny fraction of a millimeter on the dial where the water is perfectly warm. If you push the dial any further in either direction, you ruin the experience entirely.
That is exactly how it works. The computer runs thousands of calculations, analyzing the altitude changes, the distance traveled, and the gas emissions to figure out the exact speed profile that hits that sweet spot. It finds the mathematical compromise that minimizes pollution without destroying the bus schedule.
So we've gathered the data from the mixing bowl at the top rear of the bus, we've filtered out the rain and the parades, and the computer has run its simulations to find that Pareto frontier. What does this actually look like in practice? When the Transit Authority gets this report, what physical, real-world changes does the study recommend?
The researchers propose a highly practical two-pronged solution, and the brilliance of it is that neither prong requires a massive capital budget. Oh, planners will love that.
Right. Solution number one is the implementation of a least polluting speed timetable.
How does that change the driver's day-to-day experience?
Well, the data reveals that forcing a driver to rush between tight stops inevitably causes harsh acceleration, which we know spikes emissions. So the model calculates an ideal, smooth, least polluting speed for every specific segment of the route.
Okay.
But to allow the driver to actually maintain that smooth speed, the transit company has to adjust the official timetable.
So they might add, just 3 or 4 extra minutes to the expected arrival time at a particular destination?
Yes, exactly. By intentionally giving the driver that tiny buffer, it removes the psychological pressure of being late. The driver no longer has to aggressively brake and accelerate. They can maintain a steady, eco-friendly pace. It just smooths out the entire velocity profile of the trip. Giving a driver 3 extra minutes can literally change the air quality of a neighborhood. That is a fantastic application of data. But it is the second solution that really highlights the ingenuity of this study for me. Solution 2, relocating bus stops on slopes.
Yeah, this goes directly back to those critical driving zones we discussed earlier, specifically the ones located on steep inclines. The algorithm identifies bus stops where the heavy diesel engines are forced to fight gravity from a dead stop.
The worst-case scenario for emissions.
Exactly. So the constraint the researchers fed into the model was to see if moving the physical stop by a maximum of just 20 meters to a flatter location would make a difference.
Moving a bus stop just 20 meters. It's like taking a sprinter's starting blocks off the side of a steep mountain and placing them on a flat, even track just a few feet away.
I like that.
The sprinter's running the exact same race, but the initial energy required to explode out of the blocks is drastically reduced.
That is the exact mechanical principle at play here. By shifting the painted signpost and the bench just a few yards down the street, you prevent the immense engine strain of a heavy vehicle trying to overcome inertia on a hill.
That's incredible.
And the Transit Authority requires 0 new technology and 0 new engines to do this. You just change the starting position, and suddenly the nitrogen oxide and carbon monoxide emissions for that entire intersection just plummet.
It is a masterclass in using high-tech data collection to implement low-tech, highly effective physical changes. And it creates a better experience for the passengers too, right? Like a smoother ride, less jerky stopping and starting, and significantly less exhaust blowing into the faces of people waiting in that 200-meter critical zone.
It also has immediate economic benefits. A smoother velocity profile and less strain on the engine means the transit company saves significant money on diesel fuel and mechanical wear and tear. It's a really rare scenario where the environmental, economic, and passenger comfort goals all align perfectly.
So, if you're listening to this while commuting or maybe walking past a bus stop in your own neighborhood, think about the layout of your streets. What the Applied Computing Research Group has demonstrated here is that we don't have to throw our hands up in despair just because our cities cannot afford to replace 100,000 diesel buses by next year.
Right. There are steps we can take now.
Exactly. By leveraging IoT data, LoRaWAN networks, and smart computational optimization, we can dramatically reduce emissions using the exact hardware we already have on the roads today. We just have to be mathematically smarter about how and where we use it.
This study provides such a fascinating lens through which to view our daily environment. It shows that shifting a single bus stop just 20 meters can measurably alter a city's air quality.
Mind-blowing.
It really makes you wonder, what other tiny, invisible geographic frictions in our daily city layouts are silently costing us millions in environmental and economic damage, just waiting for the right data to finally uncover them?
That is a brilliant question to leave off on. We really hope this deep dive gave you a whole new perspective on the invisible mechanics of your next bus ride. Thank you so much for joining us for this exploration, and we hope you have a great day of learning.